Chapter 30 Quantum Physics. The objectives or the learning outcomes of this chapter are mentioned here. Let's go through them so you can have an idea of what we will be learning. You should be able to appreciate the particular nature of electromagnetic radiation. Now we will see how something behaves as a particle and as well as a wave. So something that has mass, we can consider it as a particle, but we will also see how it can behave or how it will have a wavelength. Interpret the photoelectric effect in terms of photons. You will learn what a photon is, and there is an equation called the Einstein's photoelectric equation. So what happens is when these photons or waves fall on a metal surface, it will emit electrons called photoelectrons. We will see the details later. Describe the electron diffraction and the evidence it provides for the wave nature of matter. Now this is what I mentioned previously also. Electron, we have learned it as a particle, that it is a particle, but you will see that it also has a wave nature. We will be able to calculate that as well because it can be diffracted. You have learned that waves can be reflected, refracted as well as diffracted. Explain line spectra in terms of discrete electron energy levels in atoms. When you learned about atoms, you have learned about the energy levels. Now we will see how the electrons are moving from a lower energy level to a higher energy level, and maybe it will come back. Now when it comes back, it releases energy. For the electron to go from a lower energy level to a higher energy level, energy is required. We will see the details of that. Use simple band theory to explain the different electrical conductivity of metals, insulators and semiconductors. Now this you would have not heard before. We will see the details. Now before we start this in the order, let's also go through the summary so that you can have a better idea of what you will be learning in this chapter. Okay, so here is the summary. This is at the end of the chapter. I moved to the last few pages of the book. For electromagnetic waves of frequency f and wavelength lambda, each photon has energy E given by E equals hf or E equals hc over lambda, where h is the Planck's constant. H is a constant. It's called the Planck constant. Lambda is the wavelength, E is the energy. Now you have to know this equation and how to use it. C is the speed of light or speed of electromagnetic waves. And you can see this is the equation that we use for electromagnetic waves. Frequency is f, and also you can see we come across the electron volt. 1 electron volt is the energy transferred when an electron travels through a potential difference of 1 volt. 1 electron volt. I'll show you how to convert this. You have to remember this, but there is an easier way. In case you forget, I will show you now how you can get the value. Now here this is 1 unit, here we have another unit. So how do you convert from electron volts to joules? You can use this conversion factor. Okay, so here is the way you can remember it easily. We have 1 electron volt. The sign between the numbers and the letters is a multiplication sign. So the sign between this 1 and the E is a multiplication sign. Between the E and the V also there is a multiplication sign, but we don't write it. What I have done now is E is the elementary charge. The elementary charge you have learned in the previous lessons, even in the AS class, that it is 1.6 into 10 to the power of minus 19 coulombs. So what I have done here is I have rewritten this with the value of E, the numerical value of E. You see the one here is the same one here, and I told you before that there is a multiplication sign between these two. That is this multiplication sign. E is the elementary charge, and that is what I have written here. Since it is a charge, the unit is coulombs. And then again there is a multiplication sign there, that is the multiplication sign here. Then we have capital V, the unit of voltage, volts. This is volts. Okay. Then you can see I have here 2 units now. Coulomb volt. Coulomb volt is joule. So 1.6 into 10 to the power minus 19 joules is equal to 1 electron volt. Again, you have learned this formula previously when you learnt about the definition of volt. Okay. So I am going to use this formula now to show you that Coulomb volt is joule. Volt is equal to W over Q. The voltage is work done divided by charge moved. Then I can rearrange this to make Q the subject of the equation, so that I get W over V. Now I will substitute the units. Okay, so from here onwards what we have are the units. The unit of charge, Q is the charge is Coulomb, and the work done is equal to also the energy transferred, that is in joules. This is voltage and that is in volts. So if I make J the joule the subject of the equation, I get Coulomb volt, which is joule. So 1 electron volt is 1.6 into 10 to the power of minus 19 joules. So again, simple way to convert this is, you can remember this, or you can use the value of this is this, and then you can write it like this. Again, you have to know this so that you can do other conversions. So for example, they might ask you what is 10 electron volts. Then you can use this conversion factor and convert 10 electron volts to joules, or the other way. Okay, let's continue. Let's go back to the lesson. Alright, the third point, a particle of charge E accelerated through a voltage V has kinetic energy given by this. Now again, you have learned the law of conservation of energy, which states that energy cannot be destroyed, but it can be transferred from one form to another. That means this is the energy that is given to the electron when it is accelerated through a voltage V. This is the charge of the electron, the elementary charge, and it is accelerated through a voltage V. When that happens, the speed of the electron increases. In this case, you can say it starts from rest and it is accelerated to a speed or velocity V. Therefore, in the beginning the kinetic energy is 0, and at the end, when it leaves that potential difference, it will have a speed of V. So it will have kinetic energy. When the speed is 0, the kinetic energy is 0. When the speed is V, the kinetic energy is V. Therefore, when the electron is accelerated through a voltage V, it will gain this much kinetic energy. I will show it to you with a diagram also. Alright, so here if we consider the cathode ray tube, you can see we have a cathode here and an anode here. This emits electrons. On this side the electrons are emitted. When the electrons are emitted, since this cathode is negatively charged, it will repel the electrons, and since the anode is positively charged, it will attract the electrons, because the electrons are negative. So negative and negative repels, negative and positive attracts. Now let's say the potential difference between this and this is V. You can see I have drawn it here. This is at this plate, and this is at this plate. So here we have minus, here we have plus. Then this is capital V. So in the beginning, let's say the electron is here, it's at rest, it's not moving, it comes here and then only it is accelerated, because the potential difference is from here to here. So here it's minus, then U is equal to 0, because this negatively charged, the electron is here, and then the electron is repelled from this side and attracted to this side. U is 0, then once it comes here, okay, it will be going through this, once it comes here, the speed of the electron is V. So here the kinetic energy is 0, here the kinetic energy is half mv square, where m is the mass of the electron and v is the speed of the electron at this place. And that's how we get this. The energy supplied by the potential difference V is this, and it is EV. The elementary charge times the potential difference is the energy supplied to the electron, and that energy, that is the potential energy. So that electric potential energy that transfers to kinetic energy over here. So that's how we write this. EV equals half mv square. A particle of charge E accelerated through a voltage V. Now in this case we say the voltage here is, let's say, V. Okay. Then it will have kinetic energy given by this. So the kinetic energy of the electron leaving this electric field, the electric field is from here to here. Okay, the electric field lines will be pointing from the right to the left, from the positive to the negative. So once it leaves this electric field, the kinetic energy of this electron will be half mv square. So let's say consider there is an electron here. We have drawn it here. See, this is the minus sign of the electron. Now the electron is here. So it is the one here is the electron here. What I've drawn here is the electron here. Okay. Then the photoelectric effect is an example of a phenomenon explained in terms of the particle-like photon behavior of electromagnetic radiation. Now this is what I explained a little bit in the beginning, and this is the equation for that. So let's quickly we can have a look at a diagram of this so you can understand it better. This is actually the energy of the photon. This is called the work function phi. It's a Greek letter, and this is the kinetic energy of the photoelectron, or the electron that is emitted as a result of the photon hitting the metal surface. So one photon removes one electron. When the electron gets removed, the electron is called photoelectron. Alright, so this is the formula. E is the energy of the photon. This phi is called the work function of the metal, and Ke max is the maximum kinetic energy of the photoelectron, because once it emitted, it will have the maximum kinetic energy, because afterwards it can slow down, it will lose its energy. So at the moment it is released from the metal surface, the electron, the photoelectron, because it's emitted due to the light falling on the metal surface, due to the electromagnetic waves falling on the metal surface, that's why it's called photoelectron. What happens is, when it leaves the metal surface, it will have the maximum kinetic energy, but when it travels, it will slow down. That's why we call it the maximum kinetic energy of that particular photoelectron. We can write it like this. You have learned E equals hf. H is the Planck constant, f is the frequency of the photons. You may be wondering, what is a photon? Now this is the definition. Photons are packets of electromagnetic radiation energy where the amount of energy equals hf, where the amount of energy equals, which is Planck's constant multiplied by the frequency of the radiation. The quantum unit that is being considered when electromagnetic radiation is understood using a particle model. We will see the details, so you can remember photons are packets of electromagnetic radiation energy where the amount of energy equals hf. Let's have a look at this diagram. You can understand it better then. Let's say there is a photon coming like this. The energy of that photon is hf. Now this is a metal. Okay, this is the surface of the metal, and there are electrons here inside the metal. What happens is, there is a certain amount of energy that is required for the electron to be removed from this metal surface. A single photon may interact with a single electron to release it. So what happens? One photon removes one electron. You can see it here in the diagram. Now this is the photon, the electromagnetic wave. It's coming like this. Then the energy from that electromagnetic wave or photon is absorbed, and a part of it is used to bring the electron to here. That is the energy required to remove the electron from the metal surface. So once the electron comes from here to here, so this is the surface of the metal. Once it is coming from here to here, now the electron is removed. The energy required to remove the electron from the metal surface is the work function phi. And after it is removed, the remaining amount of energy is the kinetic energy. Okay, again you can see it here. This is the energy of the photon. This is the work function. This is the amount of energy needed to remove the electron from the metal surface. Then what happens? The remaining amount of energy that was given by the photon, that was taken from the photon, that was transferred from the photon, becomes kinetic energy of the photoelectron. Okay, so you can see that equation here also. Now according to the law of conservation of energy, energy cannot be created or destroyed, but it can be transferred. The energy from the photon, part of it is the work function, which is the minimum energy required to remove the metal from the metal surface, and this is the remaining amount of that converts to kinetic energy of the electron or photoelectron. So we will see the details afterwards. I am going through the summary to give you an idea. Einstein's photoelectric equation is this, where phi is the work function, that is the minimum energy required to release an electron from the metal surface. You have to know each of these terms. In the exam papers, they have asked this question. They have asked you to write this and asked you each term. So you should know everything here. What is the work function? Now I didn't write what the work function is. It is already given here. Minimum energy required to release an electron from the metal surface. Then we will learn threshold frequency. Okay, we can rewrite that equation. All right, so we can rewrite it like this. Phi, I told you, is hf naught. F naught is what we call the threshold frequency. That is the minimum frequency required from the photons to remove the electron. So if it's the minimum energy, now let's say if this is at a minimum, then what will happen? The electron will be removed and it will not be moving out of the metal surface, because HF has to be greater than the work function. Then only the photoelectron will have kinetic energy. So HF has to be greater than HF naught. F naught is the threshold frequency for photoelectron to have kinetic energy. Okay, for electron to be moving, for electron to have kinetic energy and for it to leave the metal surface. Now you can see, if the energy of the photon, okay, this E, if the energy of the photon is hf naught, where f naught is the threshold frequency, that is the minimum frequency. When the frequency is minimum, the energy of the photon will be minimum. When this is minimum, this will be minimum, because this is a constant, it's the Planck's constant. So this is what we call the threshold frequency, f naught. Then when E is equal to hf naught, okay, so I will replace this with this, then hf naught, that is equal to this plus this, because it will not have kinetic energy. Okay, so then you can see phi is equal to hf naught. Again, we can rewrite this equation here. Then we can write it as hf, that is the energy of the photon, is equal to the work function, which is hf naught, plus the kinetic energy of the photoelectron or electron. Okay, that is the final one. Okay, now if hf, the energy of the photon, is equal to hf naught, that means if the frequency of the photon is equal to the threshold frequency, then this will be 0, because always this has to be either equal to this or greater than this, otherwise the electron won't be emitted. Okay, if hf is greater than hf naught, then there will be photoelectrons. The electrons will be emitted from the metal surface. So very important that you understand this. In the exams they have asked about this. Okay, the threshold frequency is the minimum frequency of frequency of the incident electromagnetic radiation. So that is this. The incident means it's coming at the metal surface. You have learned about incident ray and reflected ray when you learned about light waves. Okay, so this is the incident ray, it's coming at the surface, it's the incoming ray. Okay, the threshold frequency is the minimum frequency of the incident electromagnetic radiation that will release an electron from the metal surface. So it will be released, but it will not be moving out of the metal surface. So for example, if you look at the diagram here, the electron will come up to here, but it will not have kinetic energy to go out from there. Electron diffraction is an example of a phenomenon explained in terms of the wave-like behavior of matter. We will see those details. The de Broglie wavelength, even though it's spelled B-R-O-G-L-I-E, you pronounce it as Broglie. De Broglie wavelength of a particle is related to its momentum mv by the de Broglie equation. So the de Broglie equation is lambda equals h over p, where p is the momentum. Now you can find this de Broglie wavelength for anything that has mass and a velocity. Now even for a person, we will come across that afterwards, where there is a calculation in this chapter. H is the Planck's constant, it's a constant. So if you can take the mass of the person and the speed that the person is moving, then that person will have a wavelength. That is what we call the de Broglie wavelength. So you can see matter can behave as waves. That is what we are coming across here. So waves and particles, particles and waves. You will see properties for both of them. Okay, quickly I will show you. By the way, here is a photo of Louis de Broglie, and now you can see the de Broglie wavelength, that is lambda. Lambda equals h over mv. You can first we will learn this, and then we will learn lambda equals h over p. P is the momentum. This lambda is called the de Broglie wavelength. H is the Planck constant. Then momentum is mass times velocity. We have learned it before. We can write it like this. and there are some examples. Okay, by the way, here is the example of electron diffraction. You will see rings like this. When a beam of electrons passes through a graphite film, as in this vacuum tube, a diffraction pattern is produced on the phosphor screen. Can you see the small rings here? This is what you will see. See the rings? So for this to happen, there has to be diffraction. Okay, so that's why we are saying that diffraction is a property of waves. So the electron, which is a particle, is showing property of waves. Okay, so we will learn the details. First I want to give you an overview, and here you can see there is a calculation for the de Broglie wavelength for particles. The mass of it, for example here this is the mass of the electron, and then times the speed of the electron. See, the speed is 10 to the power 7. Then this is the Planck's constant. It's always the same value because it's a constant. Anywhere in the universe that is a constant. Then you get the de Broglie wavelength. Okay, and you can see here we apply it for a person, and this is what we get. And by the way, this is a mistake. This 3 should be in the denominator. The person's mass is 65, so we use the formula. H is a constant, that is this, and see this number should be here down. The speed is 3, and you will get this. This is a very short wavelength. See, the wavelength is very small indeed compared with the size of the gap. Hence, no diffraction effects would be observed. People cannot be diffracted through everyday gaps. You have learned that for diffraction to occur, the size of the wave, the wavelength of the wave should be approximately the size of the gap, or the wavelength of the wave should be equal to the width of the gap. And over here you can see for the electron it's fine. This is large, and then electrons traveling at this speed have a de Broglie wavelength of this much. We will see the details afterwards. I just wanted to show you this one. And you can see the nature of the electron, wave or particle. The electron has a dual nature. Just like electromagnetic waves, this duality is referred to as the wave-particle duality of the electron. In simple terms, this is very important. As an electron interacts with matter as a particle, the evidence for this is provided by Newtonian mechanics. You use the formulate Newton's law equations because it has a mass. You can use that, the Newton's laws, the Newtonian mechanics. So electron interacts with other matter as a particle. An electron travels through space as a wave. The evidence for this comes from the diffraction of electrons. Okay, let's go back to the summary. Still we are in the introductory part, that you will have a good understanding of what you will learn in this chapter. Okay, so we went through the de Broglie wavelength. Electron diffraction is an example of a phenomenon explained in terms of wave-like behavior of matter. The de Broglie wavelength lambda of a particle is related to its momentum mv by the de Broglie equation. Next point, both electromagnetic radiation, example light, and matter, example electrons. Now you can see here, this is radiation. It doesn't have a mass. For example, gamma ray, it doesn't have a mass. Light, they don't have a mass. Okay, but matter, they have mass. So we'll see now. Example electrons, matter, exhibit. So both electromagnetic radiation and matter exhibit wave-particle duality. Dual means two. So it behaves both as a wave and as a particle. That's why we use the word duality. From the word itself you can figure it out. See, wave and particle, two things, two entities. So you have the word duality. Both electromagnetic radiation and matter exhibit wave-particle duality. That is, they show both wave-like and particle-like behaviors depending on the circumstances. In wave-particle duality, interaction is explained in terms of particles. Travel through space is explained in terms of waves. Again, we will see the details afterwards. I showed a bit of it to you a while ago just now. Line spectra arise from isolated atoms. The electrical forces between such atoms is negligible. Okay, again, line spectra arise for isolated atoms. The electrical forces between such atoms is negligible. Okay, so remember here, it's applying for, it arises for isolated atoms. We'll quickly have a look at the theory a bit here. You can see here, these are the line spectra. we have these. We will see the details afterwards. So remember, we have emission spectra, emission line spectra, and absorption line spectra. What we see here, an absorption line spectrum formed when white light is passed through cool mercury vapor. Okay, so here you can see white light is split up into a continuous spectrum. Now here it is continuous, no gaps, but here you can see there are dark areas. Some of the colors are not here, but here you have everything, it's continuous. So this diagram A is what they are mentioning over here. White light is split up into a continuous spectrum when it passes through a diffraction grating. In the AS lessons we learned about the diffraction grating, and we will see what is emission line spectra and absorption line spectra. So we have the continuous line spectrum, then we have these two also. Keep them in mind, we will be learning, and also the origin of the line spectra. Okay. The energy of an electron in an isolated atom is quantized. The electron is allowed to exist in specific energy states known as energy levels. I explained a bit of this in the beginning. We can also see the definitions here. These definitions are very important. Okay, quantization is the concept that there is a minimum smallest amount by which a quantity can change. Infinitesimal changes are not permitted in a quantum universe. The quantization of a quantity is analogous to the idea of precision of an instrument measuring it. Okay, then wave particle duality is the principle that the behavior of electromagnetic radiation can be described in terms of both waves and photons. The energy of an electron in an isolated atom is quantized. So if it is at a certain energy level, it will have only that energy. If you consider the electron, for example, now let's say the electron is here. Okay, electron is here. Then for this is one energy level. For it to go to this energy level, this is a high energy level. So when you go up, the energy levels increase. So this is at a higher energy level than this. Then this is at a higher energy level than this. These horizontal lines represent the energy level. So if there is an electron here, always the electron exists at these specific levels, at these energy levels only. Okay, it can't stay somewhere in the middle. If it's staying, it has to stay either here, here on one of these lines, or on these energy levels. Now what happens is, when there are photons, the photons have energy. The energy from the photon gets absorbed by the electron. When that happens, the electron can move to a higher energy level. It can go up to a higher energy level. Okay. Then what happens is, when it is at the higher energy level, it is not we can say stable there, so it comes back down. When it comes back down from a high energy level, like you can see here, the arrow is down. This green arrow is indicating that the electron is going from the high energy level to the low energy level. You see the arrow is pointing down. Here the arrow is pointing up. When this happens, the electron emits photon. It emits the photon because it gives out the energy. So it emits light. Okay. So when the electron is going from this energy level to this energy level, energy is released, and it is released in the form of photon. Now this energy level, it has a certain amount of energy for this level. Then there is another amount of energy for this level, another amount of energy for this. So if you find the difference between these two, if you use E equals HF, then you can find the wavelength or the frequency. E equals HC over lambda. And if it is going from, say, this energy level to this energy level, the color you will get is purple. Here you will get blue. So from the wavelength you can figure out the color using this equation. If you know the energy difference between these energy levels, then that is E. Then H is a constant. You can find F, and you know the famous wave equation, V equals F lambda. And if it is applying for electromagnetic waves in vacuum or air, we use C equals F lambda. C is the speed of light. And then you can find the wavelength. We will see the details afterwards. Now already I am explaining a lot here. You can see in the example they give the difference between the energy levels like this, and you are supposed to calculate what that color or how much energy or what the frequency of wavelength is. An electron loses energy when it makes a transition from a higher energy level to a lower energy level. I explained this just now. a photon of electromagnetic radiation is emitted because of this energy loss. This results in an emission line spectrum. Okay, so we saw absorption line spectrum and emission line spectrum. So now you know what results in an emission line spectrum, which is when the electron goes from a high energy level to a lower energy level, and when this happens, it releases energy in the form of a photon. The photon has energy. A photon of electromagnetic radiation is emitted because of this energy loss. Then absorption line spectra. Now remember, we had the continuous line spectrum. We saw emission line spectrum. Now we will see absorption line spectrum. Absorption line spectrum arises when electromagnetic radiation is absorbed by isolated atoms. Okay, so here it is talking about the electron, but here it is talking about the isolated atoms. An electron absorbs a photon of the correct energy to allow it to make a transition to a high energy level. So here the electron goes from high energy level to lower energy level. It emits energy, but here the energy is absorbed from the photon and it goes from the lower energy level to the higher energy level, like what we saw here. So from here to here it is absorbed. So as a result, what we get is absorption line spectra. You can remember this easily. Here for the absorption line spectrum, the energy is absorbed by the electron. An electron absorbs a photon of the correct energy. But for emission, it's emitting light photons. So here the electron emits energy. Okay, it gives out energy in the form of the photon. The frequency f and the wavelength lambda. So it's actually explaining this and this. Okay, what we saw just now. Okay, next one. The frequency f and wavelength lambda of the emitted or absorbed radiation are related to the energy levels E1 and E2 by the equations. Okay, so this is the difference between the energy levels E1 and E2. Then also equals HF. F is equal to C over lambda. You can write this and these equations. In solids, electrons can exist in energy states within broad bands separated by forbidden gaps. This band theory can explain the different electrical behaviors of metals, insulators and conductors. We will learn about this when we come to the conductivity. Okay, let's quickly have a look at it. I think that's the last point in this summary. This is what we will be going through in detail. Okay, you can see it's here. Okay, band theory and electrical conduction. See the forbidden gap here. Then we have the valency band. Now in the insulator we have this. See, this is for the insulator, this is for the metal. So this is what we will learn. Then for the semiconductor also. Okay, if you see this thing, the last point. In solids, electrons can exist in energy states within broad bands separated by forbidden gaps. You see the broad bands. So we have here conduction band, valency band, and then there is a gap in between, which is called the forbidden gap. Okay, then again you see valency band, conduction band, then the narrow gap. Okay, so this is see energy level. So this is where you have the electron. I told you before, the electron cannot exist between those energy levels. Over here, these lines we learned before. Similarly, we have that here, electron energy. Here we said energy. Okay, forbidden gap, we will see the details. You have to know the meanings of whatever words in these paragraphs that are in green bold letters like this. What is forbidden gap? What is energy band? They can ask you what is band theory, conduction band, valency band. All these are very important. You have to know the meanings. The meanings are given here and also in the glossary of this book. So make sure you memorize it with understanding, because in paper 4 they can ask you to write the definition, they can ask you to write the meaning, and if you try to write it in your own words and miss certain keywords, you won't get the marks. When they are checking the answer that you have written, they will look for certain keywords. That's why we ask the students to memorize it with understanding, so that you will not miss the keywords that they look for in the definition for the particular words. Okay, so so you see broad bands can exist in energy states within broad bands, conduction band, valency band, so then separated by forbidden gaps. This band theory can explain the different electrical behaviors of metals, insulators and semiconductors. You saw those diagrams. Okay, so let's go into detail now. Alright, so back to the beginning. Let's go through this quickly. Okay, so modeling with particles and waves. Particle models. Now the particle is at the microscopic level. We can't see it with our eyes. So if it is something that we can't see without using an instrument like a microscope, then we say it is at the microscopic level. But if it's something that we can see, for example, you can see here these balls can be seen by our eyes. So this is at the macroscopic level. So to explain something in the microscopic level, or to explain something in the macroscopic level, we can use the microscopic level. For example, if it comes to a gas, we have pressure, temperature and volume of a gas. We can explain this in terms of the kinetic theory. Kinetic theory means it will be at the microscopic level, where it deals with particles. So temperature, pressure, volume, those are at the macroscopic level. That's what basically is explained here in this chapter. If you want, you can read the details. Okay, and previously you have learned about the kinetic theory. We learned about gases even in the A2 class, and also in the O-level classes we have learned. Cambridge O-level and IGCSE classes we have learned about the kinetic theory. Okay, I'll just go through this bit. We can picture gas molecules as small hard particles rushing around and bouncing haphazardly off one another and the walls of their container. So you remember the zigzag movement, the haphazard movement, the random movement. You learned about Brownian motion earlier. This is the kinetic model of a gas which we studied in depth in chapter 22. We can explain the macroscopic or large scale phenomena of pressure and temperature in terms of the masses and speeds of the microscopic particles. This is a very powerful model which can be refined to explain many other aspects of behavior of gases. Okay, so you can see pressure, temperature in terms of the masses and speeds of the microscopic particles. Alright, so here is a table. This table shows how in particular areas of science we can use a particle model to interpret and make predictions about the macroscopic phenomena. This is what I mentioned earlier. So we use the particle model to interpret and make predictions about the macroscopic phenomena. Let's go through some examples here in the table. Electricity model, flow of electrons. Macroscopic phenomena is current. Gases, remember kinetic theory. Then macroscopic property, pressure, temperature and volume, very easy. Solids, crystalline materials. Then mechanical properties, radioactivity, nuclear model of the atom. Macroscopic phenomena, radioactive decay, fission and fusion reactions. Chemistry, atomic structure, chemical reactions. So you can see these things, okay, or you can feel something at the macroscopic level. Particle models in science. Then wave models. So basically this is explaining about the shape of the wave. Now if it's a perfect wave, then you will have the shape of a sine graph. For mathematics you would have learned the cosine, the sine graph. Those are sinusoidal. The shape is called sinusoidal. If it's a perfect wave, that is what you get, but in reality you don't get it like that. But however, it is a useful picture, the perfect shape, the sinusoidal shape, because it can be used to represent some simple phenomena. Okay, and we learned about superposition earlier in the AS lessons. Waves are a way in which energy is transferred from one place to another. In any wave, something is changing in a regular way. Remember, waves transfer energy. Okay, we have progressive waves, they transfer energy. In any wave, something is changing in a regular way while energy is traveling along. In water waves, the surface of the water moves up and down periodically and energy is transferred horizontally. Okay, here is another table. Table 30.2 shows some phenomena that we explained in terms of waves. A sound wave, varying quantity, pressure or density. The particles become closer together and move away from each other. So that is where we have compressions and rarefactions. When the particles are closer together, we can see the pressure is greater or the density is greater when that is at the compression. Then at the rarefaction, where the particles are further away from each other, the pressure is less. For example, in a gas, let's say sound waves in a gas, then when the particles are further in the same volume, then the density is lesser. Okay, lesser mass in the same volume. Okay, which reduces the density. Density equals mass over volume. So if you have lesser mass, lesser particles in the same volume, the density will be lesser. Then light and other electromagnetic waves. Varying quantity is electric and magnetic field strength. Electromagnetic waves have the electric fields and the magnetic fields perpendicular to each other. They will, the particles, the wave is also moving perpendicular to both the electric field and the magnetic field. So the oscillations in the electric field and the magnetic field are perpendicular to each other and also perpendicular to the direction of the wave. I think when we were learning the AS chapters, we saw a diagram of this as well. Waves on strings, displacement. So the part of the string moves up, part of the string moves down. So they move from the equilibrium position. Okay, so displacement. Wave models in science. Again, this is just to explain to you so that you have a general idea. But the most important things I mentioned in the beginning in the introductory part. So you already learned that all waves show reflection, refraction, diffraction and interference. Waves themselves do not have a mass or charge. Since particle models can also explain reflection and refraction, it is diffraction and interference that we regard as the defining characteristics of waves. So this is important. Diffraction and interference that we regard as the defining characteristics of waves. If we can show diffraction and interference, we know that we are dealing with waves. Figure 30.3. So here is figure 30.3. A diffraction grating splits up light into its component colors and can produce dramatic effects in photographs. We saw a diagram of the diffraction grating when we learned about waves in the AS lessons. And we learned a formula also, n lambda equals d sine theta, very important formula. Okay, then again about the particle, wave particle duality, we will see some details here. Alright, so this part generally they won't test you on that. Here this is about the history that they are explaining what happened. See, does light travel as a wave or as a particle? And then most scientists became convinced that light travel through space as a wave. So this is about the history. It's not, you won't be tested on this. Okay.